Okay, so next up is Jeff Gordon. Jeff Gordon is at MSR Montreal and also a professor at Carnegie Mellon. And he's not gonna talk about quantum stuff, which seems cool, but this also seems cool. So he's gonna tell us about learning for policy improvement.
Thank you. And I am happy to talk quantum with anyone in the break. It's just that it wasn't quite ready for like actual slides. So yeah. So this talk is about a problem that I think is also important, which is learning from less than 1 billion examples when you're trying to do reinforcement learning. So we all know about the billion example successes of RL, and they're great. But what if experience is really expensive? So there are obvious cases where this is true, like a robot in the real world, or safety. But maybe less obvious is, like, for example, personalization. I was trying to do RL for a personalization task actually just this past week. And you know, you can't wait until the person's been using your system for 7 years before you offer personalized suggestions, right? It just doesn't work that way. And so what I'm gonna propose here is to replace sort of SGD-like algorithms, like policy gradient or DQN, with algorithms that are based on policy iteration to get a different trade-off between computation and data. And so there's no free lunch. We're not going to be able to do away with the need for data entirely, but we're going to hope to make more efficient use of the data that we have. And as sort of motivation, consider something weird about TD lambda. So TD lambda is great as well, but if you think about it, every time it does another step of stochastic gradient descent, it has to get one new experience, right? One new transition in the world per step of optimization. And so that couples optimization with data collection. And so if your optimizer happens to be slow, as SGD sometimes is, then you use more data, and there's not really any reason why that has to be true. So what if we did more computation on a mini batch of samples in order to determine a better update direction, right? If we do it well, we collect a perfectly sized mini batch. We do a fair bit of computation on it because it's worth that if the data is expensive, and then we update to a policy that's farther away from where we currently are. So what does that look like? So the exact policy iteration algorithm looks like this. We alternately evaluate our policy and improve it. So so in order to evaluate, for every state action pair, we run our policy a whole bunch of times, starting with that state action pair, and calculate the expected total cost. That's Q of SA. And value is the expectation over the actions that we take of that Q, so it's a state value. And then the advantage is the difference between the value for taking a given action and the value that we get on average over that state. And so it could be either advantage or disadvantage. An action could be better or worse than our current policy. And then, for every state in parallel, we pick the best action, the one with the best advantage, and we switch to it. Now, this is great if we're in a small problem, but in a real-size problem, we can't afford to iterate over every state action pair, and we also can't calculate the advantage exactly. We have to estimate it somehow, and we also can't change policy freely because we have to work in some hypothesis class of possible policies. So what do we do instead? So here's a meta-algorithm. This is not an actual algorithm. We can alternate, again, between evaluation and improvement steps. And in evaluation, we're going to use some kind of function approximation to estimate our advantage function, and some other kind of function approximation to to train a policy that achieves good advantage. And then we're going to do improvement. We're going to adjust our policy towards this new, better policy. And so this is a meta-algorithm because we have to specify how we're going to do the estimation of advantages, how we're going to train, and how we're going to make our steps. But at this level of detail, we can already do a simple analysis of approximate policy iteration. One is, so the observation is that it's basically for free from the performance difference lemma, that the cost of the new policy has this, oh, I can't get a, all right, I'm going to have to do the old-fashioned kind, which also isn't working. All right, I'm going to wave my arms. The cost of the new policy is that expression right there, which is, we get it, v pi of S0 is what we get for following our old policy, starting from our initial state. And then every time we take an action that differs from our policy, we gain or lose according to the advantage of that action. So if we do it t times, we get t times the expectation of that advantage, right? And so what that means is that if we have gotten a policy whose expected advantage has the correct sign, we do better, right? And so that happens when our policy isn't already optimal, our hypothesis class is rich enough to represent such a better policy, and our training actually succeeds. Now there's a small problem, which is that the expectation we're taking here is under the distribution of the new policy, not the distribution that we use to collect data. And so there's a difficulty there, but we can still develop algorithms that guarantee improvement. So there's two sort of qualitative ways to improvement that correspond to the two classes of algorithms that I was describing. In an SGD-like algorithm, we make small updates, and then if the new policy is close enough to the old, because we made a small update, then the difference between the new and old improvement directions doesn't matter. And the advantage of that is that we make frequent updates, we keep compiling information into our policy, and that's great. But it has the disadvantages that I mentioned. On the other hand, if somehow, through some other mechanism, we can guarantee that we have a good advantage, it doesn't matter how close the old and new policies are. And so the advantage here is that we might be able to spend more time optimizing each mini batch. This gives us a range of algorithms from aggressive to deliberate. So let's look at some algorithms that actually can be instances of this meta-algorithm. And there are some old ones and some new ones. So natural policy gradient, turns out you can put it in this framework. Suppose that we represent our policy with an exponential family, and our evaluation step is to fit our advantage function by regression. We have to use compatible function approximation, right? This is sort of a well-known characterization of natural policy gradient. The data, we run our old policy. We collect examples of state action pair to observed advantage. And so while we're running our old policy, we can either at each state try every action if we can reset to that state, or we can experiment using some random action selection, and then use inverse propensity scoring to correct for our exploration distribution. And in order to calculate the advantage, that's just a baseline, right? It doesn't matter if it's a biased estimate of the value. We can use any estimate we want. And then, once we have this estimate, we do what looks like a boosting step. We just rescale our policy in proportion to our estimated advantage and renormalize. And you can analyze this in the gradient descent way by showing that this value estimates the natural gradient, therefore is an instantaneous improvement direction. Or you can attempt to take a bigger step by convincing yourself that you have an estimate that is actually got the good advantage. And that second one would be a nice research direction. I like, in particular, a functional gradient version of this same algorithm because we can use any function class we want to try to get a policy with better advantage. And what's interesting is that this algorithm can't get stuck in some sense, right? It's a globally optimal reinforcement learning algorithm because if you think you're stuck, you're collecting more and more data from the same policy, you can afford to use more and more complicated function representations to try and get an advantage, and so eventually you get unstuck if you weren't optimal. It might take a very, very long time, right? It might be that you're not visiting the state that you need to get an accurate advantage estimate for very often, but that's the breaks when you're trying to explore in a real problem, right? There's no way to get around that exploration might take a long time. All right, another example is conservative policy iteration. So this is, again, a well-known algorithm. In this case, instead of an exponential family policy class, we have a mixture policy class. We actually use the exact same way, potentially. So we do cost-sensitive classification, and one good cost-sensitive classification algorithm is to do regression to estimate the advantages and pick the argmax in every state. But now, once we have this estimated advantage, we just do a mixture with the new policy. Take a small step so that it doesn't change too much. And it turns out that you can analyze this by showing that it's a Frank-Wolf update, that you've gone to effectively a corner of the set of representable policies, and you're moving a little bit towards the best corner, which is a Frank-Wolf step. To get now, so these are algorithms that take small or small-ish steps. To get a bigger step, we can make a connection to imitation learning. So imitation learning is basically just like RL, just like policy improvement, except we only do one step of policy improvement. At least that's one way to think of a lot of different imitation learning algorithms. And so we're actually not trying to do as well as the expert. We're trying to do at least as well. And in fact, we might wind up doing noticeably better, which is not something that people usually point out in the imitation learning papers, but it's an important point. So here's an example of an imitation learning algorithm. Again, our policy is a mixture class. We have some base hypothesis space, and we randomize among those policies. But this time, our evaluation and improvement steps are mixed. They happen at the same time. We're going to use no regret classification. In other words, we're going to use a learning algorithm which is aware of the fact that its training distribution is changing under it and is guaranteed to perform well despite that. Once we have that idea, it's effectively trivial to show that we get improvement because we just run, for example, we just run our no-regret learner until our no-regret guarantee, the error that we have in that, is smaller than the observed improvement in our policy, and we can switch to it, right? Or we can use the strategy in the original Aggravate paper, which is to slowly mix from the expert to the learned policy, and you can show if you do that slowly enough, you're good. All right. So I think I said most of this already. Yeah, so I guess I just wanted to point out that you have a no-regret guarantee from whatever algorithm you're using, let's say online mirror descent, and you can compare that, you can precisely calculate what your expected difference is for switching, and if that's bigger than your uncertainty, then you're good to go. Oh, and another point is, as the original paper points out, the no-regret learner will come up with a mixture policy, but we can just test each component of that mixture and use the best one. So there's no reason you can actually use the base hypothesis space instead of the mixture. And there's a variant of this that we've experimented with recently, which is kind of nice. It basically throws caution to the wind, right? It just throws a deep net in as your function approximator and is very aggressive at updating your policy even when you don't have a guarantee. And with those settings, even though you lose the guarantees, in practice it seems to perform really well. So here's an example where we do better than the expert. So what we did was we got an expert for demonstration by running TRPO overnight on one of the AI gem environments. And then we run separately, in just a few minutes, this aggravated algorithm to try to imitate that expert. And you can see that RL from scratch gets nowhere. That's the dotted lines, whereas the solid blue and green lines, they start working really well, really fast, and eventually actually beat the expert. Another nice thing you can do with imitation learning. Another nice thing that you can do with imitation learning is run it on a POMDP and let the expert cheat, right? So this is a fun way to do RL, right? Your expert does not have to be implementable. Your expert could be actually a real expert who you have to go pay to consult and you don't have them at test time, or it could be an algorithm that cheats and peeks at the hidden state of your POMDP. And as long as they're imitatable, you're not going to do better than the expert, but you can do quite well, as shown here. And again, that flat line at the bottom is ordinary RL. And so at the time scale of this, the ordinary RL has gotten precisely nowhere. All right. What I wanted to advocate today is that we look at algorithms within this class, right? So there's a ton of combinations that I haven't had a chance to try, and that there's more than I could possibly try in a lifetime, because we have so many different ways we could estimate the advantages, represent our step directions, or choose to improve our policies. And there's this trade-off from aggressive to deliberate updates that we would want to make separately for each new domain. But I think it's potentially a really productive class of algorithms, because it holds the possibility of wringing more information out of each new sample. I also want to be clear that this is not solving the exploration problem, right? This is an algorithm for doing as well as you can with the data that you have, and we got to solve the exploration problem, right? So I guess I should also advocate that in parallel we think about that. But these could, I don't know, it seems like if you're able to think more for each new policy update, it's potentially a good venue for experimenting with exploration methods. All right, so I think that's what I wanted to say, so I'll stop there and thank you, and I'll take questions.